Welcome to Concepts of Formal AI. Since this is the first episode, I will do a brief introduction. I am Dustin Giuliano, and I have been promoting Formal AI research since at least 2019. I major in computer science and am currently specializing in research for programming languages, type theory, and formal methods. This series is not a set of lectures, but short, high-level demonstrations, experiments, and conceptual overviews intended to onboard fellow researchers and developers into the challenges and future ecosystem of formal AI. This first episode is the most important basis for formal AI, simply stated as AI equals program. This correspondence will be shown through a demonstration called Artifact 1, which I encourage viewers to download and try on their own. Before we begin, though, I want to leave a note for the future. As of 2026, which is when this video is being recorded, the premise of this talk is that we can equate AI with a computer program. This is not widely accepted at this time, even resisted. However, I think this notion of AI's programs will be taken for granted and become quite normal in the future. And I wanted to say this now because I would like others to remember that this was quite difficult to convince people of in the present. And it took me quite some time to simplify this idea into a short demonstration that is both easy to understand and communicate. So with that out of the way, let's begin. The foundation of this episode is observational equivalence. It is the idea that two systems, or programs in our case, are identical in terms of their input-output relations. There is no discernible difference between their externally observable behavior. When two programs are observationally equivalent, it does not mean that they are equal. To be equal, we would have to define what we mean by that, and the usual notion is exact equality or perhaps isomorphism. These could be interpreted in various ways, but they would be structural in nature. In our demonstration, the two systems are very different structurally, and that is part of what makes it interesting because they are nonetheless identical in their input and output pairs. This leads to a perspective shift. For the purposes of this discussion, let us suppose that machine learning models are akin to interpreted computer programs. This will become more clear in a moment as we progress through the slides, so bear with me a moment. Because under this view, we obtain some important correspondences. The first one is that training models becomes analogous to program search. By program search, I mean broadly the act of exploring and exploiting the space of all possible computer programs and their associated data. The important point is that it is not limited to one particular method. Another correspondence is that model inference is analogous to bytecode evaluation. This is not the only correspondence, but it is useful for this demonstration, as you are about to see. Two models will now be introduced. These are both from Artifact 1. A link is in the description, and there will also be a QR code at the end of the episode for others to download and replicate this demonstration. The image you are seeing is a one-to-one exact representation of a PyTorch PT file. Each pixel is 1 byte. The luminosity of the pixel is its value, with darker going to 0 and lighter going to the maximum value of 255. This file is about half a megabyte. The model you are seeing in this image is a 4-layer MLP, a common type of artificial neural network. This model takes a short sequence of input symbols and produces a compressed run-length encoding as its output. It is intentionally overfit so that it obtains 100% accuracy. That is not a limitation, but by design, as perfect observational equivalence with the second model was a requirement to prove the point of this episode. There are multiple reasons why I am presenting the model as an image. The first is that it visualizes the information that defines the model, including its weights. And the second is that it is utterly incomprehensible to us as humans, and that is one of the key points. Lastly, while this model is open weights, it should not be considered truly open source AI, as source code that would correspond to this image is not available. I do not consider the training program to be this model, so that does not save it from the distinction I am making. This will become more clear in a moment. This is model number 2. I put the word model in quotes because this is also a visualization of another binary file. It is just a lot smaller. Let's magnify it so you can see the pixels. This model is only about 500 bytes. However, the comparative sizes of these models is not the focus, and it is not a fair comparison anyway, because Model 1 is essentially the machine learning equivalent of a lookup table, and this model is a general algorithm for run-length encoding. They are both identical in their observable behavior on the closed universe that has been defined. That input universe is every permutation of 8-character strings containing the letters A and B. Both of these models are observationally equivalent with identical input and output relations. This is effectively a proof by exhaustion via brute force verification. The input domain was specifically chosen so this would be tractable, and though it makes the MLP in Model 1 very specialized, it demonstrates the observational equivalence to Model 2. They are literally the same in terms of their functionality. The demo program for Artifact 1 shows how these two systems can be swapped out for one another, and, all else being equal, an observer looking only at inputs and outputs would not be able to distinguish between them. The important point, though, is that both of these models are difficult or impossible to understand, as you saw in the images, and, alluded to previously, Model 2 has another representation, one that Model 1 does not have because it is an MLP. The image of Model 2 you have been looking at so far is not actually an artificial neural network at all. In reality, it is an exact-to-data visualization of a Python bytecode file, and the exact source code that produced that file is on the right. This source code is fully complete. There's nothing more to it, and it fully describes the bytecode you are seeing on the left. This is the model. And this is one step towards understanding what I mean when I say AI equals program. There's a little more to it, but this is a good starting point. Now the blue arrow here indicates something much stronger than observational equivalence. These two representations are equal in some sense. It is still not an isomorphism because of some information loss, like comments. However, they are semantically equivalent and have common substructure that can be perfectly mapped between these representations. This brings us to the lesson behind the episode. In Formal AI, the quote, models are literally human-readable programs and data. In fact, in order to be considered Formal AI, the programs and data must be human-readable. It is not enough to just produce any program in any language. The target languages, code, and data must be in a form that we can understand. And by understand, I mean in aggregate. This is because sophisticated Formal AI models in the future, or their solutions, may be millions of lines of code, far beyond the ability of any single human to follow. However, working in teams, as we do now for large software and hardware projects, the hope is that we will be able to understand and verify an AI of that level of sophistication. Now, being able to target formal languages has a lot of potential benefits, and here are a few to get started. The first is reliability. We will be able to leverage the power of constructive mathematics, intuitionistic logic, and type theory to prove, not merely test, that AI we create adheres to its specification and is free of unintended behaviors at runtime. The next major advantage will be transparency. We will gain the ability to understand the AI that we or other AI create. This also allows us to extract knowledge from the AI itself. And I would like to encourage all of you to see code as a form of knowledge, not unlike a specialized kind of digital book. The last benefit is perhaps one of the most exciting ones, which is that we will be able to train once and reuse. In this paradigm, since AI is just code, we can import modules and create a global library of AI subsystems. This will lower costs, barriers to entry, and accelerate global AI research and development. There's also the efficiency afforded by targeting any kind of formal language. This means we can use optimal data structures and algorithms, and target new and existing hardware, even custom integrated circuits or exotic forms of computation that exploit physical degrees of freedom. The demonstration behind this episode is called Artifact 1, and it is freely available for download. It is completely reproducible, will construct its training data, create the models, and has comprehensive evals. This should help convince any skeptics that these two models are indeed observationally equivalent. To conclude, we introduced observational equivalence, presented two different models, one of which was MLP and the other Python bytecode, which was revealed later. The models have identical observable behavior, exact input-output relations. The idea of AI equals program was asserted and then exhibited in an exhaustive proof using Artifact 1. This hopefully established the correspondence between AI and computer programs. Formal AI acknowledges this reality and seeks to construct AI that we can understand and verify. Thank you for watching, and please remember to like and subscribe if you enjoyed this presentation, as there is more to come.